All right. So today we are starting electrostatics in person. I hope most of you have watched the video, but I will revisit some of the material from last class. So that means today we are going to formally arrive at Gauss's law, and we will also have to formally establish the relation between Gauss's law, the electric field, and the potential. So one thing that we will have to do, and that is we have to solve this uniqueness theorem that says that, and unfortunately there are many uniqueness theorems, just like there are right-hand rules. This particular uniqueness theorem says that if you have some kind of an arbitrary field, as long as you know what the curl and the divergence are of that field, you have uniquely specified the field. That is, of course, very important because the way we establish electric and magnetic fields is through Maxwell's equations, which is all about knowing what the divergence and what the curl are of those fields. So it's a rather important thing. So we will do that. Then afterwards, you can actually not only show that it uniquely defines the field, but you can also invert that relation and then say, well, if you know the divergence and if you know the curl, can you go in a straight way from the divergence and the curl to the field? So solving Gauss's law directly. And of course, that is possible too, but it's going to take some math. And of course, I need to mention that uniqueness theorem says nothing about gauge invariance, right? So it says that the curl and the divergence uniquely establish the field, but it doesn't say that the curl and the divergence themselves are unique, because we know this. If you have an electrostatic potential, you can add a constant to it because the potential really has this gauge freedom. And there's a similar thing for the vector potential. So we will work that out. And then I hope that by the end of today, we will have done most of the hard parts of the electrostatics, and then the next class we will do energy stored in the field and the energy in general associated with electrostatic charge configurations, and then we should be done. I don't really want to do the multipole expansion because we end up not using it much to begin with, and it's fun to know that it's around, but other than showing you the formula for the multipole expansion, we're not actually going to use it for anything. So I'm going to skip past that. So let's talk about electrostatics. And of course, electrostatics starts with Coulomb's Force Law. So the Coulomb Force Law. It says that if you have some kind of a charged object here, some little q1 and some little q2 here, that there is a force that is acting on both of these charges that is described by this force, which q1, q2 over r12 squared, and it is pointing in the direction of the vector that joins r1 to r2, and that vector r12 is by definition r2 minus r1. And let me fix these. So 2, 1, 2, 1, 2, 1. So we can also write it as using the fact that the vector is always the unit vector times the length. Stick that in there. You can also write this obviously as q1, q2, r21 vector divided by r21 length, but now that's cubed because of that extra factor of length. Then if we have more than one charged object, so more than one charged object, superposition says that you should be able to add all those forces. So let's say you want to know the force on 1 due to 2 and number 3 and number 4, etc., 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 would be the force on that first charged object number 1. What does that mean? Well, the force on some kind of a charge with a question mark would be the sum of I over all the other charges of that Q with that question mark that you're placing in some kind of configuration that has already been set up, where you take the sum, this is the unit vector I. And for all of those other charged objects, the force contribution to that is going to be proportional not only to that charged object Qi, it's also proportional to that Q that we're evaluating the force on. So we can factor that Q out. So some kind of a Q that is now placed in the configuration made up by those charges. And of course, that is the definition of the electric field. So this is the electric field. So let's write that down. Then that means the electric field is the sum over all charges. The charge is QA. The distance to that QA, actually, let me write this explicitly as an electric field. It's evaluated at some position R. And now we need to divide by the length cubed. And that is, of course, for a distribution of charged objects. And of course, a single charge would have some kind of a E as a function of R, would be just whatever that Q is, R hat, over R squared, if it's at the origin, or more general, if it's at some specified position R prime. And this is for a distribution of point charges. It's not too hard to generalize this for a system of some kind of a charge distribution. So then we integrate over the charge density, and we still use that same distance dependence. So we still have some kind of an R minus R prime divided by R minus R prime cubed, and we integrate that over all of space. Okay, new expression. So point out the things that are the same. So this guy plays the role as this guy, and the rest is just that distance and vector formula that gives you the right direction of the field. And this is, of course, integrated over dx, dy, dz primed. Now, for a point charge, oops, you can say that if we know the electric field, it's some Q over R squared R hat, we can actually write that as minus the gradient of Q over R. If you work out your math, you'll see that you're absolutely allowed to do that. And what that means is that is actually minus the gradient of phi, where phi is the potential. So let me use that. Where phi is the potential. And it's the potential of a point charge. So phi is just some Q over R. And now for charge distributions, there are again the same equations. Let's say if it's a set of point charges that you place your that you want to evaluate your potential of, you gotta find out where all of them are and then just divide by the distance. So this is R minus RA distance. So this is for discrete. And of course, it's an integral rho R prime R minus R prime d3x cubed. So this is a volume integral, meaning you integrate over all of space. So strictly speaking, there's supposed to be two more integrals. So E is minus the gradient of that phi. And then note that these are all direct integration solutions. All right. Another approach to finding E. So let's look at the point charge again. So we know that for such a charge, the electric field is just whatever that Q is, R hat over R squared. All right. Let's calculate the divergence of E. Okay, well, the divergence of E would be the divergence of that one, it would be Q R hat R squared, which would be, so plugging in here, the gradient, the R component of the gradient is 1 over R squared, dr R squared acting on something. And because it's all in the R direction, that's the only component we need. So, all right, let's do that. We have a 1 over R, oops. We have a 1 over R squared, ddr R squared. And now we're going to put in the actual thing. So there's a Q here over R squared. And of course, you see that this R squared, they cancel. So that means that the right-hand side here of this equation is 0, but only if R is not the origin. Okay, so divergence of E is 0, we're all good. However, what if we take the volume integral of this thing? So let's take the volume integral of E, and we're integrating over all of space. So we're taking that thing and we're sticking it in here, and we're integrating that. So this is, however, and we can rewrite that as an integral over the edge of the volume that we were integrating over. So this was integrated over some volume V, and we can integrate it over the edge of that volume. But we then have to take the dot product with ds. Okay, and then for a sphere, you just get 4 pi r squared q over r squared, right? Because the electric field is the same over the entire surface of the sphere. So we can just factor out the surface area of the sphere. And now again, you see an r squared and an r squared canceling, and you get 4 pi q. Now, look very carefully. This is not the same as 0, which is what we would expect based on the fact that if you calculate the straight up divergence of that 1 over r squared, it's supposed to be 0. So how can we reconcile these? Well, we have to realize that the exception is the origin. We already know that we are not allowed to look at that divergence in at the origin because it's not really defined very well. And we do know that as long as that sphere that we take our Gaussian integral around, as long as that spans the origin, we know that on the right-hand side, we're going to get a 4 pi q. So this is a textbook case of a delta function. So we say that the divergence of E is actually 4 pi q times the delta function of R. If it is a point charge at the origin, oops, no, at the origin, or generalized, if this holds for a point charge, we should also be able to just take 4 pi rho for some kind of an arbitrary charge distribution. Charge density distribution. All right, and of course, this is Gauss's law. AKA Maxwell 1. Now that we have this expression for Gauss's law, we can also write the electric field as the gradient of the potential. So remember, minus the gradient of the potential, that means therefore that the second derivative or a Laplacian of that potential is also that 4 pi rho, except of course now with a minus 4 pi rho. And this follows straight from Gauss's law, and it has its own name. This is the Poisson equation. And there's a special case where it's 0, or rho is just 0 everywhere. And then it is known as the Laplace equation. And of course, the symbol we also write as this. We saw that before, which is the Laplacian. So now we're going to use this fact that if you take the Laplacian of Q over R, we know that the right-hand side is going to be minus 4 pi Q and then delta R. We're going to use this fact to very quickly determine what the Fourier transform of 1 over R is. All right. Well, let's walk through this. Let's first look at the question a little bit carefully. When I say use the fact that something is something to calculate quickly the Fourier transform of 1 over R, what I'm therefore asking you to do is not explicitly evaluate the Fourier transform, but use this identity as a shortcut. So you don't have to actually execute this Fourier transform of 1 over R. The second thing is that you should know now, because we've done it a couple of times, that if you take the Fourier transform of the gradient working on something, I just made a green squiggle, that's the same as taking I times that k vector times the Fourier transform of whatever it is that operator was working on. And if then in that identity that we had worked out for the potential, you set that Q is equal to 1, what you now have is the Laplacian of 1 over R is equal to minus 4 pi delta R. So because that holds, we can take the Fourier transform and it should still hold. So working out the left-hand side of the Fourier transform of that identity, the Fourier transform of the Laplacian of 1 over R is going to be 2 factors of I, k vector that you then, of course, square and take the magnitude of, because there's a dot product in there. So you get minus k squared times the Fourier transform of that 1 over R. But we're not actually explicitly evaluating that Fourier transform. So that's the left-hand side. And the right-hand side, well, you take the Fourier transform of a delta function. What you end up with is just 1. But there happened to be a minus 4 pi in front, so we carry the minus 4 pi. So the right-hand side is minus 4 pi. So putting everything together, we therefore have that the Fourier transform of 1 over R is 4 pi over k squared. Okay, so that type of exercise is really where I need you to be mathematically throughout this semester, and that means also towards the end when midterms and finals come around. So if you're not conversant in Fourier transforms, I don't think that's a word, but anyway, if you don't speak it fluently, you gotta brush up on it, because we're going to need it a lot. And it's not just that Fourier transform; it's also the fact that we're throwing a lot of higher level math around. We're going to do that a lot, so get ready. The nth uniqueness theorem, or how we solve Gauss's law and be confident it's right. Okay, so what does that uniqueness theorem say? Well, let's say we have some kind of a vector field. So some vector field V. And let's say we know that the divergence of that V is some kind of an F, which is now a scalar field. And also that we have the curl, which is a vector field. And now the uniqueness theorem says that, let me actually write this explicitly as a function of R. So this is R. So it says that F and W uniquely determine V of R. That's what it says. Note, it does not say the reverse, aka gauge freedom. Right, because we know that we can add things to it. Okay, so these are the two things that we have. So I'll get this one, this two, and once we have those, it's supposed to uniquely determine that vector field V. So as an aside, note that this is the general form of Maxwell's equations, right? Because we have 4 pi rho, we've got a curl of E minus ddt of B, and we have something similar for B, 0, oops. Zero, it's 4 pi J over C, 1 over C, ddt of E. Right, so the that vector field V on the in this statement could be played by both E and B in Maxwell's equations, and that scalar field V, that scalar field F for the Maxwell's equations involving the electric field, this would be F, or this would be F. And this would be W. All right, so what we're going to do is we're going to say, does it really make sense that the right-hand side here, which are the source terms, uniquely define the fields? And that's what we're going to do. So go back to this. So we're going to do this, but we'll do it as a demonstration of the reverse. So we'll say, let's say both V1, which is a function of R, and V2 as a function of R are solutions to 1 and 2, then that means that the uniqueness theorem says that, oops, that V1 must be equal to V2. Okay, well, what does that look like? Well, that first expression, the divergence of V1, which would be divergence of V2, which would be equal to that first scalar field. And we know that the curl of V1 and the curl of V2 must be equal both to that same vector field W. Well, if they're identical, then if we subtract 1 from 2, so we're going to make a new vector field here. That's going to be that V prime. Then we expect that V prime is going to be is going to end up being 0. All right, so let's take the divergence of that new field, V prime. We know that is the divergence of V1 minus V2. So we need the divergence of V1 minus the divergence of V2. And of course, because that's F, oops, this is F, and this is F, therefore this must be 0. Same for the curl. So going to be the curl of the difference, V1, V2, curl of V1 minus the curl of V2, which is, of course, it's going to be, oops, this is going to be W. So therefore, subtract them, 0. And of course, that's a scalar. Sorry, it's a vector 0. So the difference field is curl free, right? Because the curl of that difference field is 0. So the only freedom we still have is some kind of an offset. So let's say this difference field is the gradient of some potential field. So we're going to use some colors. Okay, this is V1, and this is psi. Of course, this is not V1, this is V prime. Okay, so V1, that's the difference field. And this is the potential, the difference potential. All right, so we know that with this definition, because the difference potential is defined through that gradient, if we take the Laplacian of that difference potential, that's the same as taking the divergence of the difference field. And we know that the divergence of that difference field is 0. Okay. And then we're going to invoke one of Green's identities that says that the volume integral of this combination of these two functions or scalar fields integrated over the volume is equal to the volume integral, sorry, the surface integral over this. And now we're going to use F1. F2 is going to be that difference potential. Okay, so we're going to rewrite this identity. So it's V. F1 is psi, and F2 is also psi. So this is the Laplacian of psi plus. So I'm just putting it in. And this is, of course, the divergence of that field. So this one is this. That's where we are right now. Divergence of that field, but that's dotted with the divergence of F2, but F2 and F1 are the same. So this thing is just squared. Integrated over the volume is right-hand side. Integrated over the edge of that volume of psi, gradient psi, dotted with the normal. All right. Now we're going to put a little bit of a bound on this, and we're going to say that assume that that difference field goes to 0 as r goes to infinity, at least as fast as 1 over r squared. So if it goes faster, it's good. We can have it go faster. This implies that the difference potential must go, because it's the gradient, must go at least as fast as 1 over r. So first order, second order, it's important. So there's a 1 here, 2 here, because we take the gradient, right? All right, so that means that the right-hand side, which says the following, we have this over the edge of the volume, psi, gradient psi, dotted with ds. Okay, this one is going to go like 1 over r at least. And that means that the gradient, which is of course the difference field, at least 1 over r squared. So that means that that thing you're dotting with the normal of that surface together goes like, oops, 1 over r cubed at least. And we know that the surface is going to go like r squared. So that's good, because that means that when r goes to infinity, we have an r squared over a 1 over r cubed, so it can never explode. So it goes to 0 as the volume goes to infinity. So ultimately, things will be all right. Okay. Now the left-hand side. Okay, left-hand side. Well, we already know that this one is 0. So all we need to do is figure out what that yellow underlined term is. Well, the yellow underlined term, that's the, we're doing the volume integral. Integrated over the volume. This is the same as, by definition, V1 length squared integrated over the volume. because of the definition of V prime, because of the definition of the difference field. Right, so that goes here because, no, come on. V is the gradient of that difference field. Okay, so now the left-hand side says that the magnitude of that difference field squared, integrated over the entirety of space, must be 0 by the time you reach the end of space. So the right-hand side says that this is 0. So this is the length squared. Now there's no way that you can come up with any kind of field that has, let's say, a little blip somewhere off by Mercury, because in the end, you're adding length squares. These are all positive numbers. So in order for that entire integral of length squared to be 0, that means that that difference field must be identical to 0. So V1 is the 0 field, and that means that V2 is equal to V1. We are done. Now that we have a proof for a sufficiently confined field, can we solve it? So in other words, let's say we have the divergence, which is F R, and we have the curl, can we basically take these and say V is some function with F and some function with W? So we have to figure out a way to invert this equation. And hopefully by now, you know that when we have differential equations and we're trying to invert them, so solve them as general as possible, our workhorse is the Fourier transform. All right, so let's do that. So let's say we have 1, 2. So we're going to start on number 1 first. So we have we're going to take the Fourier transform of both the left-hand side and the right-hand side. So the left-hand side, of course, is this divergence of V, and the right-hand side is F of R. And the left-hand side becomes I, K vector, Fourier transform of V. And this is still right-hand side, Fourier transform of F of R. And now we're going to write that explicitly as dot product K with the Fourier transform of V, which is now, I'm going to indicate this with a squiggle. So V, which is a function of K. And this is F of K. So this is the same as this. That's what we call it. And this is the same as this. All right. And I'm missing an IK, and I'm dividing by I, and 1 over I is minus I. So that's what identity number 1, which defines the divergence of that field as that F, looks like as in reciprocal space or in Fourier space. So let's do identity number 2. Take the Fourier transform, and now again Fourier transform. Now we take the curl V, and the right-hand side is, of course, that field W. And now that means that I have an IK vector crossed with, now this is again the Fourier transform. Okay. Okay, that's the left-hand side. And the right-hand side is going to give you the Fourier transform of that W field, which is then again indicated with this squiggle over it. And now I'm moving my I over to the other side, so that becomes a minus I, and it disappears there. Oh, oops, let me use a different color. So remember that this is one of those triple product rules. Is A dotted with C, B vector minus A dotted with B with C. So we're going to use that. So we're going to say K vector crossed with K vector crossed with VK is by the identity that I just wrote down in green, that's on the left-hand side, that is K dotted with Fourier transform, K, that's a dot product, minus K squared, because A and B are both K, VK. All right. Now we know that this is minus I F of K. We know this is K squared. We know this is WK with an I. Okay. So now we can solve for V. The Fourier transform of V. It's going to be I, K vector crossed with W. I'm going to stop drawing my, maybe I'll keep one, minus K Fk, and the whole thing is divided by K squared. So this follows all from that same expression. So now we have V, we should be able to do the inverse transform. Let's take the inverse transform. So we're going to have the inverse transform of V. It's going to be the inverse transform of, here we go, I, K crossed with W over K squared minus the inverse transform of K, Fk also over K squared. Okay, the left-hand side is what we want. So this is actually the field that we're trying to solve for. So all we now need to know is what happens on the right-hand side. Well, let's use our trickery box. So we have an ik vector, and we're going to change the ik vector into a Nabla operator, because we're allowed to do that. That is the W field over K squared. And I think I'm missing an I somewhere. Yeah, I. This is the inverse transform of that field over K squared. So let's look at this one first. The gradient of the inverse transform of f over K squared, this is still the Fourier transform, is therefore the gradient of the convolution of the reverse transform of f and the reverse transform of K squared. So that's going to be gradient of the inverse transform of f, okay, convolved with the inverse transform of 1 over K squared. Now we know what the inverse transform of 1 over K squared is because we just did that before the break. That's just 1 over R magnitude. So therefore, this is the gradient of some kind of a scalar field G, where G is built of that convolution, which we can write explicitly as follows. So this is F R prime, and this is R minus R prime, integrated over all of space. So that's your convolution integral, and then there's a 1 over 4 pi. Okay, so again, this inverse transform became this F, and this inverse transform became this 1 over distance. Okay, so that's the left-hand side. And the right-hand side, sorry, the rightmost side of the right side, and the leftmost side of that side does something similar. So let's write that down. We have the curl of the inverse of that W field over K squared. And that is, because it's a product of two functions, you can write as a convolution integral. And this is the field U, where U is a similar convolution integral, W R prime, less than R. Divided by R prime. Okay, so we have finally, and again, this thing here, the 1 over K squared, the 1 over K squared became this thing. And of course, the W showed up here. So we now have the inverse we have V is minus the gradient of some field G, and the curl of some field, some field some field. Why am I not able to write this? Where the G and the U expressions are given by those two convolution integrals. And I'm missing a 4 pi here. Let's see. Okay, let's check this for Gauss's law. So we're not using the circuital law yet. Well, we know that V is supposed to be minus the gradient of some field G, and G is that convolution integral of this right-hand side F with R vector d cubed x. Okay, well, let's see if that works. If this is E, which would be minus the gradient of the potential, where the potential is 1 over 4 pi F, and F would be, F is the divergence of E, and the divergence of E is 4 pi rho, so that's 4 pi rho, and this is R minus R prime d cubed x prime, and that's cool because these two cancel. And this is our regular definition of the potential for an arbitrary charge distribution. It's just rho as a function of R. So that is exactly the same as what we had before. But now through the inversion of the uniqueness. That's phrased a little weird, but basically saying I have the divergence and I have the curl. How do I solve that? And this needs to be fixed. That wasn't there as I was writing it for the first time. Okay, well, with the sun in my eyes, we've made it, we inverted it, we showed the uniqueness, we've done most of our electrostatics. So that means on Thursday, we will do the energy in the field, and then I believe we are done and work in moving charges around. And then we're done. And that's going to be, hopefully, if things don't go bad, the last class that we do on Zoom. So that means the week after, we're going to be back in person. Now, I plan to make recordings of those in a classroom. I don't really quite know yet how I'm going to do that because I have to set up something. But I'm sure we'll get it to work. I do expect everybody to come in person unless you are forced to isolate. But yeah, I'm going to need to see all of you. So looking very much forward to that.